on your homework, there's a little example problem where you just simulate the circular or elliptical orbits based on initial conditions. You can actually test your code or reuse the solutions online, kind of tailor that code to your liking, how you want to do it. For the first part of your homework problem. But keep in mind that's only part of the problem. So here's the initial conditions. I've got an R of 42,000 kilometers from the Earth. So imagine the Earth is here. The Earth has a radius of 6,000 kilometers roughly, so it would take up about this much space. And I launched a satellite into what should be a circular orbit. So I set up the initial conditions of the geostationary Earth orbit that we learned about last class period. 42,000 kilometers from the Earth. I just started it at 0, so it would be here along the x-axis. And you'll launch it this way. So the initial conditions are, well, it's circular, so there should be no R component of velocity. So you see that's 0. And I calculated using that formula, remember the formula from yesterday, square root of GMP over R is your theta velocity component. I came out to 3.1 kilometers per second, 3,100 meters per second for a geostationary Earth orbit satellite, and I launched it with that tangential velocity. And then I just want that set of difference equations to do the work. And it traced out a beautiful circular orbit. And sure enough, 23 hours and 56 minutes later, it got back to the exact same point, confirming that this is essentially a geosynchronous Earth orbit. Now, many of you, when you're going to do this exercise at home, will have something that looks like this. Here's your planet. You'll start your simulator, and you will get this. What is wrong? If you're using this technique to simulate the time progression of your orbit, what is likely wrong? Can anybody think of some culprits? Yes, that's usually exactly what it is. Remember, this is a discretized system of equations. It's not modeling the disturbances in between the samples. And so, the smaller your delta t, the more accurate it's going to be. At some point, if you make your delta t so big, it's not even going to close up on itself. Now, there's a trade-off there, right? It takes a lot longer for really fine delta t's. For this type of differential equation system, a delta t step of about 5 seconds will work for pretty well for Earth orbits. You'll calculate it, your computer will calculate the entire orbit in a matter of seconds, and it'll almost always close up reasonably. Okay, let's try another example. What does this look like? What happens if I give a weird set of coordinates, a skewed set of coordinates? 30,000 kilometers as my starting point over here. 0 degrees, I'll always start it on X because there's always rotational symmetry. I always tilt it if I'm going to start it at a different angle. Without loss of generality. That's how you write that in the textbook, right? Without loss of generality. We can take any orbit and say it equals to 0. And then look, I gave it a kind of a skewed set of initial velocities. Both the R and the theta component have different values. 1 kilometer per second in the R direction, that would be here, and 2 kilometers per second in the theta direction, that would be in that direction. So you can see, now surprisingly, when I give any orbit with a non-zero v theta component, you're guaranteed to have something elliptical. And that's what we have in this case. It's a nice elliptical orbit. Here's another one. This is a highly eccentric orbit. Look what I did on this one. These are all actual homework problems, by the way, that I gave years ago for the class. So, okay, I started off at an orbit of 6,000 kilometers. So pretend you're on the surface of the Earth. And let's also pretend that there's no air resistance, right? I launch at 8 kilometers per second d sub r and 1 kilometer per second d sub theta. So it's almost like heating a projectile up in the air. You see it goes up and it goes down, sort of in a limit of very small initial velocities. Replicate what the Newtonian mechanics of Earth-based surface gravity would predict, right? Lobbing a projectile up in the air to kind of fall with a parabolic trajectory if there were no air resistance. And of course, your computer's dumb, right? It just keeps going. It's going to go all the way to 0, even though this is like, it would be lava at that point. And of course, I'm always a sticker, right? Like, faculty always have fun with their students. I didn't teach this, when I gave this assignment, I didn't teach this, but I gave them these initial conditions. So look, you're roughly on the surface of the Earth. We're using Earth-based gravity. 12 kilometers per second. Condition that was greater than the escape velocity for the planet. See, one of the nice things about gravitational potential is that you can impart enough energy to actually break orbit. It didn't have to work out that way, right? It could be a 1 over r to the higher power law or lower power law that didn't work out that way. Folks live in this wonderful three-dimensional world that makes it so that you can actually send spacecraft outside of your planet. And so the escape velocity of a planetary system, v escape, is basically 2 times constant over your starting initial R. Take the square root. Okay, any questions? So the goal will be to have some fun with this. You'll have to play around, you get started on the little code, pushing around the orbit. Then what you want for these dynamic equations, not only do you understand the orbit, but you have to have the time evolution, which is a bit trickier to calculate. It's more of the simple Kepler's laws. But by doing this, you can work through, and if you get your code running, when you learn about look angles next week, you'll be in good shape to finish off your homework in fine style, in fine fashion. Okay. Any questions before we go to the next topic? Yes, you did. Can you solve it in a continuous time? Not using any functions that you or I would be familiar with. There are some special functions that are kind of tabulated just for this type of application that you could use for it. But in terms of like transcendental functions, you know. Divide the second equation by data. Yes, it's tricky because they're coupled in a peculiar way, right? Because there's also a data dot here, and there's some cross dependencies for those. So you can actually would involve elliptic functions. It's easier to program different equations to calculate your orbital evolutions. Good question. Very good question. Anyone else? In a very complicated 3D, multi-body, imperfect world, we'll talk about this highly idealized orbital mechanics framework that we've learned as electrical engineers trying to be satellite communications engineers. Where does it break down? You know, it's interesting that these simple Keplerian laws capture 99.9% of the behavior of the orbits. And the rest of the deviations are important to understand. And you need to understand, you know, how you're going to correct those, how you're going to change them. But those usually don't impact the communication system in any significant way. Right? We're going to be doing link analysis on satellites. So we need to know where the satellites are. We need to know how much physical distance do we need to overcome for path loss. What angle is the signal going out to the atmosphere in order to figure out where it's going to wind up. Small disturbances in orbits, as electrical engineers, we view that as somebody else's problem. So, and my aerospace engineer is always agreeable. Thank you. That's somebody else's problem. But, you know, we should still be aware of what those problems are. How is it going to impact? Because everything in a satellite system impacts one another. That's the beauty about a satellite. It's a heavily constrained design problem. So you may call it electrical here. I don't need to know about aberrations. And then it turns out that the station-keeping fuel that you need is going to limit your total spacecraft lifetime. Because you're going to need a certain amount of station-keeping fuel to overcome these degradations and aberrations in your orbit. And that's going to determine how long that your solar panels have to last, and how much power they have to be providing at the end of their lifetime to drive your electrical system, which may be operating off of something that's similar. So I often liken satellite system design to hammering out the lumps on a carpet, right? You knock down one lump over here, and two more pop up over there. In places that you weren't expecting, your power constraints or your communications design, or you say, oh my goodness, I have to have 30% more station-keeping fuel because this orbit needs more correction than I was expecting, which means my antenna can be 2 kilograms, has to be 2 kilograms less. Which means I just lost 2 dB of gain, which means I no longer can modulate this way. And I mean, it's this kind of endless dialogue and trying to optimize the best spacecraft for a particular utilization. If you do it right, you save your company millions of dollars. So it's important to understand all of these things. Now, where do these disturbances from our pristine two-body problem come from? Well, one of the disturbances is from a third body. And so what are the other bodies in the solar system? Let's rank it from most influential to least influential. What's the thing for Earth orbit satellites that's going to disturb the orbit the most? The moon. It's not the biggest object in the solar system, but it's by far the closest. So the moon, which is 385,000 kilometers from Earth, radius centroid to centroid. What's the next thing? What's the next body in the solar system that's going to influence Mars? Not quite, no. The sun. The sun is 150,000 kilometers, 150 million kilometers, much farther than the moon, but of course much more massive. And so that's why it comes in as a close number 2. A close second to the moon. When it lacks in distance, it overcomes into sheer mass. What's the third thing in the universe, or in the solar system? In the universe. That influences and tugs beautiful, perfect circular and elliptical orbits out of whack. The third thing, not Mars. Mars is chintzy. It's tiny. What's the next biggest thing in the solar system? Jupiter. And then everything else is kind of in the noise. Usually inconsequential enough where you can ignore it. These are the three big ones in this order for Earth-based satellites. If you start doing deep space missions, it's usually these two things. And depending on where you are in the solar system, they probably swap order of importance. Jupiter is almost, it's not as massive as the sun and it's farther away, but it's almost like its own star. People who study planetary and solar system formation suggest that Jupiter is a would-be star. A lot of stars are binary in nature. In other words, the solar systems of other places are 2 or 3 stars, and we have a single star system, which is not unheard of, but quite often there's another object that turns into a star. Jupiter just didn't quite make it in our solar system. Didn't quite make it. Okay. Now, this is a source of perturbation for Earth-based satellites, other bodies. There's another source of perturbation, and that is actually the Earth itself. Earth irregularities. There are 2 types of irregularities about the Earth itself that influence the satellite orbits. One is the shape of the Earth. The Earth is actually not a perfect sphere. It is what scientists call an oblate spheroid. And that is a But if you put a satellite up there for 10 years, and you let these errors accumulate day after day after day, you'll actually notice a difference. In fact, it's an oblate spheroid instead of a perfect sphere. Yes. The south hemisphere. A little bit more mass down there than it is in the northern hemisphere. Strange as that may be to contemplate. As a percentage of the mass of the Earth, it's not that significant, but even which if the Earth is 6 times 10 to the 24th kilograms, a few hundred trillion kilograms here or there doesn't make much of a difference in absolute sense, but it will actually distort the gravitational pull slightly with errors that will build up over time. So Earth irregularities. The other irregularity is something called mascons. Mascons are regions on the Earth that have different densities. So, for example, let's take a look at the polar view of the Earth. So this is the North Pole. We're looking down at the North Pole. The Earth is spinning this way. For the absolute space, if we ignore the rotation of the Earth, and this is something that is really only important for geostationary Earth orbit satellites, the mascons. Why? Because those are, they need to maintain exact synchronization with the rotation of the Earth, and they need to have the same alignment with the latitude of the Earth that they started on. And over time, even slight changes, remember these things are moving in thousands of kilometers per second, right? And so if you impart even a slight error, like half a meter per second, builds into your velocity. Over time, that satellite will drift out of its design longitude and place in the sky. And you'll lose the whole reason why you launched a geostationary Earth orbit satellite to begin with. And so there are, because your phase locked in the Earth, if you were in a lower Earth orbit satellite, this wouldn't be a big deal for a lot of reasons. First of all, you're always moving, so you're going to have to deal with some tracking anyway, right? Secondly, you're moving around and around the Earth, and whatever irregularities are on the Earth will try to cancel each other out over time. Not true for the geostationary Earth orbit satellite, because you see the same part of the Earth all the time. So there's an irregularity, a higher density region on one part of the surface of the Earth than the other. Over time, that irregularity will build error up into your orbit. And so it turns out that there are actually 2 stable points, regions of high-density mascons that attract the geostationary Earth orbit satellite, and the 2 unstable points. Let me just write where they are. The unstable points are at 162 degrees longitude and 348 degrees. These are unstable points. And then 75 degrees and 252 degrees. These are stable points. And for the top on in terms of longitudes, so 360 degrees or 0 degrees, this would be Greenwich, England, roughly. here you have North America. Here's North America. Here's like Central Asia, India, Pacific Ocean, and Europe over here. Europe and the Pacific Ocean, very repulsive. North America, Central Asia, attractive, right? I'm just kidding. But that's what the stable and the unstable points are. If you have a geostationary Earth orbit satellite here, over time, it will slowly, without any correction, start to drift. If it's over here, it moves this way. If it's over here, it moves this way. It'll probably oscillate a few times before it gets there. Likewise, if it's over here, everything will start to approach that stable point over there. And left to their own devices, over the course of many centuries, you would develop these two giant trash stars over the Earth, where all the dead satellites would accumulate. But obviously we don't see that. So as part of an international agreement, if you launch a geostationary Earth orbit satellite, before the satellite dies, you need to make sure there's enough station-keeping fuel to launch it into something called a graveyard orbit. And so you only need to go about, 200 kilometers beyond geostationary Earth orbit. There's no drag up there, so you're going to stay in that orbit in perpetuity. And that piece of space junk will have just enough motion, slower than the surface of the Earth, so that all the mass comms will integrate out and it won't fall into those stable points. So to launch a geostationary Earth orbit, you must make sure there's enough station-keeping fuel to put it in that graveyard orbit. Any questions about that so far? Okay. Now, a couple other things to keep in mind when we talk about the extra bodies that influence the tug and pull of satellites in orbit. I said earlier, we had a really good question earlier. Well, are all the things in the solar system lined up on a plane? Like, the planets all operate on the same plane? There's nothing to, kind of. But there are some disturbances. So let me quickly sketch out two systems to show you kind of what the angular disturbances are. They're not going to be to scale, but they're just for reference. So let's say this is the Earth, and this is the rotational axis. Not to be confused with the magnetic axis, which is slightly off. But this is the geographic North Pole, and this is the geographic South Pole. And so 90 degrees to that would be the equatorial plane. I've drawn it as a line. It's a plane that comes out of the board and is perpendicular to that rotational axis. Now, a geostationary orbit satellite, we said, had to be on that plane to be geostationary. You can launch satellites at different angles and different planes, and that plane is called the plane of inclination. So when we talk about inclination, we're measuring the angle of an orbital plane from the equatorial plane. 0 degrees would be equatorial. You can go all the way up to 90. That puts your orbit poles. You can even go past 90. If you go past 90, we call that orbit retrograde. Because effectively what you're doing is now rotating against the rotation of the Earth. Those are actually more expensive orbits to launch into, because not only, usually you launch everything going with the rotation of the Earth, because you get a little bit of a boost of kinetic energy. Because you're starting out on the Earth, you're rotating in that direction already. It makes sense to kind of launch it in that direction, otherwise you have to overcome that kinetic energy and then add that kinetic energy back, and then launch it into enough, give it enough energy to launch it to an orbit. And so for the most part, everything is, most things are in a inclination launch of less than 90 degrees. There are some applications, we'll learn about a couple of them. You want to launch in a retrograde orbit, have things go against the surface of the Earth, or the rotation of the Earth. So anyway, this is inclination. The moon, the natural satellite of the Earth, is at an inclination of 5 degrees. This is why we don't get those solar eclipses that often. Because usually this isn't even lined up with the solar orbital plane. And so then if you go down and look at the Earth-Sun system, so the Sun actually has an axis of rotation. And it is roughly lined up with the plane of the solar system, but the Earth is actually 7.3 degrees inclined from the Sun in its orbit. And then the Earth itself, of course, has a tilt of 23 degrees. Its axis of rotation is actually 23 degrees off from its orbital plane with the Sun. And of course, the Moon is going to be plus or minus 5, depending on where it is in the system from that. So it's going to kind of wobble around. But only when things kind of line up perfectly, you get things like lunar eclipses and solar eclipses.